Good morning. As promised, I will finish up the derivation of the Planck radiation law. Actually, it's the Planck function itself. Now, I want to point out an error that I made, I mixed up my notation. That G is actually an N. We define this to be G of nu. That's the way I did it. So, I'll recap most of this stuff as well, but just to point out this little error, it's the N by the nu, not the G. The G itself is defined to be this object, and I'll show you where that came from. And this is as far as I got. Planck assumed that we have harmonic oscillators lining the walls of the cavity radiator, and they generate waves of energy integral numbers of h nu, 1 h nu, 2 h nu, 3 h nu. Nowadays we know it's n plus a half h nu, but that half wasn't known in that particular time. Now, I'll recap. We did the classical case which have a partition function which is continuous. Continuous becomes discrete when we have discrete energy levels, right? Discrete, beta n h nu, and beta is 1 over k t. K being Boltzmann's constant, T being the temperature. But this is our discrete partition function. Now, the expectation value of the energy is what we get when we put the energy in here, and it's En. There they are up here as well. And that we can write in the exact same way, and I'll do this in a minute. Now it works out the same way as I did the discrete case. We can make sure that say that this is the same as 1 over u du by dx. Okay, we use that little relationship here, and it's the same thing over here. I'm going to erase the board now, and I'll start doing the Planck case because I want to show you how this gets resolved. I will do a recap as well of the whole thing from beginning to end because there's a lot of stuff to get your head around. There's even more. So, the Planck case. So we got this object here. And we have that object, we had that change made. Go and change your notes from the last video. So, here is our result so far. And that is that the average energy is given by minus d by d beta summation from n equals 1 to infinity of all the oscillators e to the minus beta n nu, where beta is 1 over k t. So that's so far so good. Now let's look at this. Which was it? Let's expand this guy out in a binomial series. In a binomial series, what do we get? Well, we get for a 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed, etc. Where x is minus x and n is minus 1. N is minus 1, x is minus x. So therefore we get 1 plus minus 1 times minus x. Okay, so far so good. Plus minus 1 times minus 2 over 2 times minus x squared plus minus 1 times minus 2 times minus 3 times minus x cubed over 3. Factorial. 3 factorial. 2 factorial. Okay, so what does that give us? It gives us 1 plus x. 2 over 2, and minus times minus is plus, times minus x squared is x squared just. So, this is 3 factorial over 3 factorial, also gives me 1. Minus times minus times minus times minus. 4 minus is a product, x to the 4th. So therefore we see that it's 1 plus x squared plus x to the 4th plus x to the 5th plus, and so on. So we're going to let x equal e to the minus beta h nu. So x squared is just that, x to the n. So it is that. This is a summation of this thing here. So this expression here is this thing here, right? Sigma that is sigma that. So, get your head around that, because I need to erase this, or at least I'll erase this. Yeah, you got that? This, this, this. Sorry, this is a log in here. Right. So now we take the log of this guy here. Now with the minus sign here, we get a log with a minus sign. Of just 1 minus x. Now I slow down on signs because keeping track of signs is the most difficult thing in physics. So we want to keep our track of signs. It makes a big difference. We get a plus. So, take the derivative of log 1 minus x, it's 1 over 1 minus x times dx by d beta. Now don't forget what x is. X is this. And when we take its derivative, there's an n in here. Yeah, so there's an n there. Take the derivative and I get minus n h nu all over 1 minus e to the minus beta n h nu. So far, so good. Minus times minus gives me plus. So that's our expression. I'm going to multiply above and below the line by e to the power of plus beta n h nu. Now this times this with a negative and a positive gives me 1. So Don't need this. On the top I just get NH nu times 1. And on the bottom, this times 1 is itself. And this times this, positive and negative, sorry, that's a positive. And that's a positive 2, gives me 1. And I get the Planck function as required, and it's very neat. Yeah? So I hope you guys followed that. So I'm going to write the final result now. So this is our final result. And I'm going to put it up here. So get your head around that quickly, because I need to take it off the board. We're running out of time. I'll just remind you what we did before. Now, U is the number of states times the energy per state. Like I said, if a state has an energy of 10 joules and you have 100 states, 10 hundredths is 1,000. 1,000 joules is the energy of the system. Now that's when there's no spectral dependence. If there is a spectral dependence, we have to integrate over the whole spectrum, and we'll integrate with respect to nu. Spectral dependence of N times the average energy. Not quite, because we need to go d by d nu N. So now the d by d nu is what we've just found. It's this guy here. Now I forget, was it 8 pi nu cubed over c cubed I got for the average energy? Let me check. Nu squared. Now this is the average energy per state. I got that previously. And now we've just got an expression for the N by d nu. This is the g nu, the Planck function. So we've got our result. Let's get rid of this. G of nu now I can't remember which was let me just check. This is not correct. This is the average energy E. So this is the G of nu. This is the G of nu, and this is the dN by d nu, the E. Sorry, I'm sorry. I mean, I put that in already. I forget why I made that mistake. But that's my E. And this is the E. So we can put in the results. Sorry. Growing up like that. Now I also think that this is u over v, yes. We divided out the volume earlier, so this is a little u. Right? Okay, I'd forgotten I'd taken the derivative already with this thing here, because that's squared. It started off as a 3, and there was a 3 downstairs. I'd forgotten I'd done that. Okay, so there we go. That's the result. I'm going to recap it now for the record. So let's have a quick look at what we were doing. That's the end result. So basically this is what we're looking for. For the continuous case, we have that expression for the partition function. And we got kT, okay? So kT was the average energy that goes in here, and the n by nu is still this guy here. That one there, right? And we get Rayleigh genes. Now for Planck, we have oscillators. And the continuous integral goes over to becoming a sum, and the new q we put the En equals nh nu in here with the new q, and we get the exact same kind of an expression, right? We replace this with the sum. So E and we work out the average energy, and we find it to be equal to nh nu over e to the nh nu minus 1. That's our Planck function. And in both cases, we have this result. Where did we get this from? Where did we get that from? Okay, I'm going to remind you. This is our E for continuous. This is our E for Planck. The Planck radiation law will use this E. But let's see where the G nu came from. G nu is related to the density of states. We assumed that the waves in the cavity radiator were standing waves with the number of modes big N. So we solve the wave equation. Strictly speaking, by separation of variables, so we get psi in a box of sides L. So volume of the box is L cubed. And these ends are discrete. Integers. So therefore then, when we operate on this with the wave equation, I get n squared, let's see, pi L omega squared over c squared. So now we get a sphere of radius r whose volume we need an octant because we're taking only the positive ends. R cubed is going to be L omega over pi c cubed. And omega cubed is 2 pi f cubed. So when we work out this, we get an expression for n, the number of particles inside that octant of the sphere, and then we take its derivative to find that dn by d nu is that. dn by d nu is 8 pi nu cubed over c cubed squared. I think this is squared. Yes, it's squared. Okay? And that's where it all came from. Now I need to do some problems. I'm going to do some problems and applications, but that's for the next class.